So our next speaker, I believe, online is Krzysztof Wohlfeld from the University of Warsaw, Altermagnetic polarons, the title of the talk.
Yes. Hello, hi. Can you hear me?
Yeah, we can hear you.
Okay, so I share the screen. Can you see it? Can you see the screen?
Yes.
Yeah. Okay, good. Thank you. So yeah, so let me start here. So basically, yeah, two apologies. So first of all, I have changed the title. So it's because I decided to give a bit broader overview of the topic. And so that's one point. And the second, I really apologize for not coming. It would be really great to be there. So I'm really sorry, and I'm also unhappy myself. So let me start now with the. Okay, does it work? Yeah, okay, it works. Um, Let me start with a kind of a very short preface to the problem. So basically, as also we have heard today and yesterday, and you all realize, so most of the research on altermagnets is focused on the weakly correlated altermagnets. Yeah? And the main reason is that these are the best for applications. That's where the field has basically started. And so for spintronics, for instance, especially. And that's one point. The second point is that also, for all ab initio method, DFT kind like ab initio methods, it's really the best here, because we are on the safe ground. But there are also some negative points here that one can mention when one looks at the weakly correlated altermagnets. One is that we restrict ourselves only to a certain pool of materials. So always finding candidate altermagnets to study maybe, well, is an issue, of course, still, as we have heard, with this ruthenium dioxide by Rose earlier this morning. And where in the end of the day, it looks like it's not an altermagnet. And the second point is that if we look at the microscopic mechanism, then in the weak coupling limit, it's usually not so easy to determine what really causes magnetic interactions there, apart from some really simple mean field or some phenomenology. So that's on the weakly correlated. If we go to the strongly correlated altermagnets, on the other hand, well, there are, of course, two main issues here. The first one is that these are really not good for applications and not where the field really has started, because these are either mod insulators or bad metals. That's one point. And second point is, of course, DFT or even DFT plus U kind of calculations are not good here. But on the other hand, what is good is that it's another route to obtain additional automatic materials. And also, quite often we can have quite a good understanding of the microscopic processes which lead to the altermagnetics here. Okay, so I will concentrate in this talk on this second class of materials, on these strongly correlated altermagnets. And the talk will consist of three parts, basically. So in the first part, I will introduce one subclass of these strongly correlated altermagnets. These are the Lieb lattice systems. Then I will go to another class, which are I call them AF, AO, meaning antiferromagnetic and alternating orbital systems. And then finally, in the last part of the talk, I will actually tell you something that I have promised initially, which is on the altermagnetic polarons, or in other words, being more practical on the ARPAs on altermagnetic mod insulators. Okay, so that's the outline. Okay, so let me go to the first part of the talk, which is on the altermagnetic mod insulators, and on this class number one, let's call it. So basically, so these are the so-called, I call them Lieb lattice systems. So we can introduce these systems by looking at the Lip lattice that has also been discussed here during the workshop, where what you see here, these are, if for those who are familiar with the copper oxide studies, copper oxide geometry, so these would be typically transition metal ions, the red balls here, and the blue ones are the ligands, if we want to look at the coming from the copper oxide community, let's say. And so this is a sketch of the Lip lattice, and now imagine we introduce a Hamiltonian for the Lip lattice, which is a Hubbard-like Hamiltonian, and now it's actually in the so-called anti-cuprate limit, meaning that we have a large Hubbard U on the B and C, so on the ligand sides in the cuprate language, and we have no Hubbard interaction on the red side, so on the Hubbard, on the copper sides in the cuprate language. And so that's one main difference with respect to the cuprates. So U is on the blue, not on red. And the second difference is that the charge transfer energy is exactly opposite than in the cuprates. So this epsilon A is the on-site energy for electrons, and this is actually positive, and it's introduced on the A side. Yeah? So it's the so-called negative charge transfer limit in the cuprate language. Okay, so that's why it's called all anti-cuprate limit. So that's our starting point. Imagine we have such a we have this Hamiltonian on this system. And now, actually, like that's not my work. That was my the two works in December showing that one can actually quite perturbatively derive an effective model from this Hubbard-like model, and it turns out that this is the J1, J2 checkerboard model. So the model that you have also we have also discussed during the last 2 days quite a lot. Yeah, so that's actually kind of all well settled. One can get these J1 and J2 spin exchange interactions just exactly from that, exactly perturbatively from that microscopic Hamiltonian here. And you see this checkerboard J1, J2 spin model here. So it is clear to note now that this the ground state of this model, as you all know, is this checkerboard Altermagnet. Okay, so this way we see that this anti-cuprate model on the Lip lattice leads basically very quickly to this to an Altermagnet. Yeah, so which one can even see, you know, already by designing this model that this is what to expect here. Okay, so far so good, but the question is, you know, can we find a realistic system which actually really, you know, where this model applies to? So what actually we have tried is some time ago is that there's this proposal that maybe we can actually start with the copper oxides, and maybe we can tune the parameters in the copper oxides and go to that limit where we finally get an Altermagnet. So the sketch of this concept is here. So we start with a Lip lattice. We say, okay, we first take a charge transfer model in the cuprate limit, when we, of course, get an antiferromagnet. But now maybe we can tune this model that gives rise to this standard antiferromagnet in the cuprate. We can tune it a little bit by pushing magnetic moments onto the oxygen in such a way that they also order, yeah? Because I mean, magnetic moments are always in oxygen and the cuprate, but to make them order in this fashion may not be so too easy. And finally, so this is the so-called pi-pi Altermagnet, where we have a coexisting antiferrometric order on copper sides and oxygen sides. And then we can think of maybe we can push it even further, maybe in not so unrealistic regime of the model, maybe we can get this just an Altermagnet. Yeah, so we have no magnets on the copper sides. So that's the kind of idea. And now what we have checked actually is that we took the standard charge transfer model for the cuprates. So that is always used there. And now what we do is the starting point are the realistic cuprate parameters with the realistic Hubbard U on copper and on oxygen. And what we did there in this paper, we started tuning the parameters. And in particular, it turned out that still keeping these U's as they are, keeping the standard copper oxide hopping as it is usually used in the cuprates, turns out that just tuning the oxygen hopping, so-called TPP, a little bit by 20, 30%, let's say, we can get altermagnetic stabilized. It's super weak, but it's non-negligible. Yeah, so these are the results from ED calculations. These are the different parameters of the model, TPP, here TPD, and you see actually the orange and the blue are parts of the phase diagram where we see altermagnetism, yeah? And this is for fixed charge transfer, and this is for fixed, actually, copper oxide hopping. So actually, the microscopic origin is basically, roughly speaking, due to these spin exchanges as discussed properly in the anti-cuprate limit. But of course, here we are in a much more difficult regime, where actually we cannot really say it explicitly, derive it explicitly, so see it explicitly. So it's actually still working to fully understand the microscopic mechanisms here, especially actually for this coexisting pi-pi altermagnetism, which is even kind of more difficult to understand how it arises. We've got some ideas, but that's still a challenge for theory. But anyway, for the experimentalists, and the general message here is that we are not so far not so far from the altermagnetic regime in the cuprate compounds, just looking at the electronic Hamiltonians and electronic problems. Okay, so that's the first point. Now let me go to the second system, which is the antifermatic alternating orbital system. So how altermagnetism arises here. So first of all, it's kind of you have probably seen this kind of pictures here which is a canonical comparison of antifermatism and altermagnetism. And what you see here, immediately you can notice that altermagnetism is actually, you can realize that this is just an antiferromagnetic ordered state and alternating orbital ordered state. Okay, so it's just a tensor product of these two orders. That's kind of clear from this regime. So the question that one can ask here is actually what kind of models may give rise to such an antifermatic and alternating orbital ordered states. So that actually was discussed many years ago by Kugel and Komsky more than 40 years ago, where they introduced the concept of the so-called spin orbital models. So these are models which arise when actually the starting point are again Hubbard-like systems with many orbitals on the same site, actually not on different sites as before for the Lieb lattice. So we've got multi-orbital Hubbard systems, and when we go to the commensurate fillings, then it turns out that we end up with the so-called spin orbital models. Yeah? So these are the models which are given by the Hamiltonian as shown here. So these are of the kind of where we have the spin, typically Heisenberg interaction between spins, but not necessarily, and typically some kind of interaction between orbitals, which is usually of lower symmetry than for the spins. And this actually, these kind of Kugel-Komsky Hamiltonians, they arise from the exchange processes. So these are exactly kind of qualitatively similar processes as give rise to just Heisenberg spin exchange when it is derived from the single band Hubbard model, but it's all a bit more complicated because we have to consider two orbitals per site, and so these exchange processes, as for instance, there's one exchange process illustrated here, where we have one site here, another site, typically ionic site here, and these exchange processes are such that we have got this virtual hopping from one site to another. There's this virtual state which calls Hubbard U created, and then the so-called other electron from this lower orbital hops back to the left, and we end up with this orbital exchange due to this kind of t-square over u process. Yeah? So this is all well identified, and this leads to, and all well derived, it has been derived tons of times, and leads to these Kugelkowski Hamiltonians. So there are also tons of papers, still from 1982, the original one, and then several reviews later on during manganite hype, or when when iridates were introduced, and so on. Okay, so far so good, but what's the issue here is actually that the main issue here with this antiferrometric and alternating orbital systems is with getting them is that actually typically these Hamiltonians, they lead to the ordered ground states, which are either ferromagnetic and alternating orbital or antiferromantic and ferroorbital, but usually not antiferromantic and alternating orbital. And this is actually all summed up in the so-called good enough Kanamori rules, which are some kind of phenomenological rules, so they are not very strict, but nevertheless, they typically well describe what's really happening in realistic Kugelkowski Hamiltonians. So they actually they are fulfilled in these canonical systems like lanthanum manganite or potassium copper fluoride. So this actually means that it's very difficult to stabilize such a structure in these realistic Kugelkowski Hamiltonians. So the question is, can we find a Kugelkowski Hamiltonian which describes a system which actually has this kind of order? So actually there's one relatively well identified case which is actually the AB plane of lanthanum vanadate that's actually has been known already for many years. And so in this lanthanum vanadate, we've got 2 electrons in the 3D shell or in the 3D T2G subshell, and which form the S1 localized spin. And it's a strongly correlated system. It's a Mott insulator and with common thread filling. And it's extremely well described by one particular complicated spin orbital, Kugelkowski Hamiltonian. And it turns out it orders also, it has very well developed spin and orbital order at the same temperature of the order of 140 Kelvin. And the order that it sets in is actually illustrated here. And you see that in the AB plane, it has these alternating orbitals and alternating spins, which actually can be also viewed from above this way. So you nicely see these are the T2G orbitals alternating, but this is really a nice antiferromantic alternating orbital structure, which is exactly like this stereotypical altermagnetic cartoon. So it is really there, and it is also confirmed experimentally, so all is fine. The reason why it arises is actually it's actually kind of special. So I have this slide, but it's mostly for experts, and also I don't have much time. It's just to tell you that we have also a very good understanding why we've got this order in this particular Kugelkowski Hamiltonian, and that this actually is pretty special here in this particular transition metal oxide. So it's rather skeptical, it's not that it's the only system. Of course, one can think of probably there are other for sure, but it's kind of difficult for sure. Yeah, that's kind of clear to get this. Okay, but realistic. Okay, so far so good. So actually, how much time do I have?
5 minutes and
5 minutes.
10
Okay.
10 minutes with the questions.
With the question. Okay, good. That's fine. Yeah, I need 7 for this. Okay, so basically, so far I have basically just told you, 2 classes of altermagnetic Mott insulators, which actually, to some extent may be or are realized in some transition metal compounds. And now, so it's not that unrealistic, but now what I want to tell you is actually something even more practical for, especially for a number of you, for experimentalists here, which is what can be the signatures of altermagnetism in these mod insulators. So as you all know, ARPAS has been used to detect altermagnetism in several systems. So the question is, what if we do ARPAS on these strongly correlated altermagnets? So what we actually did with Maria and Jeroen, who are actually the driving forces here. So in this project was that we calculated just numerically the ARPA spectra on this canonical J1, J2 checkerboard altermagnet. And what you see here, this is ARPAS on this spin polarized ARPAS. This is for spin up. The spectral function, the upper spectrum, this is for spin down. Here there are different momenta. Here this is the energy for Fermi level is here. These are just occupied bands below the Fermi level. These are this is a mod insulator. Yeah? So actually, well, I used the word bands, but it's really not a proper way of describing what's happening here, because this is a correlated system, a strongly correlated system. So one should rather not talk about bands, which actually it's a single band system, but you see it's a very complicated spectrum. So there are just quasi-particle peaks here, but you see, and there's a lot of incoherent spectrum here in this ARPAS on this mod insulator. So this is actually this first point that this looks like this. It's like typical to mod insulators. So that's not something special. But what is special about altermagnetism here is that there's very strong spin-dependent spectral weight transfer. So you see this peak has very large spectral weight compared to this one for spin down. And vice versa. At another momentum, by half, you see large spectral weight here and a small one here. On the other hand, so that's one point. On the other hand, there's almost no spin-dependent shift in energies. So this peak here and this one, they are almost at the same energy, and the same here and here. It's a matter of numbers, of course, but they are very close. Okay, it's for one model. We repeated it for this other case. So this is actually for a Lieb lattice J1, J2. Now we can go to this lanthanum vanadate. So this other kind of class of altermagnetic mod insulators. This is this kind of vanadate model, and what you should and actually the story repeats to a large extent. So this is actually ARPAS for spin up. This is ARPAS for spin down on this on the model describing lanthanum vanadate. And you should look actually at the blue color, which shows ARPAS on the XZ, YZ orbitals. The red one is for the XY. So just looking at the blue color, what you see here, for instance, that there's almost no spectral weight. It almost disappears for spin down. There's a lot on for spin up. However, so this is just like before, there's also some spin-dependent shift in energies, which is observed here. So it's quantitatively a bit different, but still. Okay, so this all contrasts actually, the canonical picture that you all know of ARPAS on weakly correlated altermagnets, where the main point is actually this paradigmatic signature, let's say, of altermagnetism is this spin-dependent band splitting. Yeah? So this is here completely different. There's also this spin band splitting, but it's typically small. But the spectral weight transfer is really the signature of the spin-dependent spectral weight transfer is the signature of altermagnetism. So one can also ask, why is it so different in this? How do we understand this result? So we have a full understanding actually for this, I would say. It's but in order to really go there and describe it, one would probably need like a half an hour tutorial or so on these problems. But basically, what one can discuss here is one can introduce a simple cartoon picture to describe, to explain how we understand ARPAS on such an altermagnetic mod insulator and how the altermagnetic polaron is formed here. And basically the main starting point, the general point here is that ARPAS on a strongly correlated altermagnet actually is modeled in this way that what ARPAS does to the system is actually it kicks out a single spin, it creates a single hole in an altermagnetic spin background. Yeah? So this is very important to realize. It's completely different if we model ARPAs with DFT, we never do it. We just calculate the band structure, the electronic band structure. Here, actually, it's a many-body system, so we have to understand that the eigenstates of the system with one electron removed are completely different than qualitatively different when without this electron being removed. Yeah? So we have to study really in order to understand ARPAs on the Altermagnet. We have to study what happens if we had a hole, a single hole. We initially added here, then it propagated here to this Altermagnetic structure, this checkerboard Altermagnet. And there are actually two processes here which are important. One is that when the hole moves, it creates spin defects when it moves between the different spin sublattices. But it can also move freely on this in this Altermagnet when it moves on the same Altermagnetic sublattice. So these are the 1 and 2 processes here described here on the slide. And this process number 1 is where actually hole creates spin defects, so it couples to magnons. But you have to imagine that magnons actually, these are altermagnetic magnons, so they have altermagnetic properties. So this way, hole actually couples to altermagnetic magnons and kind of feeds with altermagnetics. And the second point is that when the hole actually moves freely here between on the same spin sublattice, this actually also moves differently depending on which sublattice it is. So it also feeds with altermagnetism. And so these are the two processes which actually work together in an entangled fashion, let's say, and they together lead to both coherent and incoherent hole motion, which gives rise to this whole complicated quantum many-body spectrum. And now, depending on the ratio of the coherent and incoherent hole motion,
Yes.
we have
2 minutes.
2 minutes, okay? So depending on this ratio of this coherent and incoherent hole motion, so on this 1 and 2 processes, the quasi-particle spectral weight peak is either larger or smaller. And at the same time, you see that these two processes actually depend on the altermagnetic properties. So this way, you see that effectively how large is this quasi-particle peak is really depends on the underlay on altermagnetism there. That's how we explain this process. Okay, so that's this cartoon explanation, and now actually one can have also a similar cartoon for the other case, which actually altogether very roughly it's a similar situation for lanthanum vanadate, so for the other class of multi-insulating altermagnets. If you want to see nice cartoons and understand how the hole moves there and how the spectral wave transfer arises, one can actually look at this short, almost popular science paper by Mona from many years ago, where actually there was no discussion about altermagnetism, but it was this lanthanum vanadate system discussed there and ARPAs on this. So it's actually all explained there if you want to understand it, but it's very similar to a large extent as what I told you. Okay, so just to conclude, so to finish, so I had these 3 parts. So one was on these Lieb lattice altermagnets. So there are several papers on this. I was involved in that collaboration with Johannes, Rose, Valentin, and Ing, who were actually really doing a lot of there, as you see, and so that's I really thank them. Then there was this actually the second point was the second system where these orbital systems, like in lanthanum vanadate. So there are a number of papers from many years ago from Gini and Kalyulin, then actually just in general on these good enough Kanamori rules. We also had a paper many years ago with Maria and Andrzej, and then recently there was this actual paper by Johannes Knolle as well on this. And finally on this ARPAs, on alternative multi-insulators, there are also a number of papers from a long time ago, but also there's this recent paper that we have with this draft with Maria and Jeroen. So you can have a look for more there. And so that's all. And finally, I just finished with this picture, which is basically almost self-explanatory. So it's a photo of me in Yalta more than 20 years ago. But maybe what this explanation is that this EU flag that we took there for this trip, was actually I got it in as an Erasmus student in Leiden, where I first met Jeroen. I didn't get it from Jeroen, but it was at that time. So. Yeah, so let me just conclude that let's hope that this dream that we had
Okay.
20 years ago,
So let's send the speaker. And one brief question, very brief. Okay.
If I can. Hi, Krzysztof, good to see you.
Yeah.
In the cuprates, it was my understanding that this ultramagnetism is related to rotation of the octahedra. Is that the case or not?
Yeah, that's also possible. Yeah, so that's what my understanding as well. That in lanthanum 2 copper 4, in the standard cuprate, that's what happens. Yeah, that there's this weak ultramagnetism because of this. However, what we are looking at here was just a standard free-band, Emery-Kiveson model, and we were tuning the parameters and seeing, okay, maybe we tune a little bit one of them, and maybe we get ultramagnetism just from the electronic, Yeah. So that's it, and it's kind of, like what I can say is that what you can imagine is that clearly, if you go to the negative charge transfer limit and also with large UP on oxygen, immediately you get ultramagnetism. But the main point was, okay, maybe we don't have to go that far, maybe just tuning a little bit we can. And it turns out that tuning a little bit we can get it. Yeah.
Okay, thank you.
Okay, there is one question online, so let's give a possibility to ask it. Okay, please.
Yeah, thank you for that's I really like that result on the spectral weight shifts that you see in the Hubble systems. So is this your idea then that in the systems that are primarily orbital ordered, giving rise to the altermagnetic order from the orbital degree of freedom, that the ARPES will show these typically more generically these strong shifts?
Yes, provided these are really correlated systems. Yeah.
I mean, from the orbital order, it will be correlated always. I don't think you're going to have
these are not
weakly correlated, not orbital order. Yeah.
So so one can imagine that one has itinerant systems, which are metallic systems with some alternating orbital ordering in the weak coupling regime.
Yeah, but that typically, as I said, they're not dominating. I don't think that will be the origin of the order itself. But the orbital ordering, I think, in the mod ones that you're saying, I think
but
that
even mod
strong effects, and I would have expected that.
I am sorry, I have to interrupt because we are far beyond. So let's send the speaker.
Thanks.